A couple of quick announcements. So I had the code review on Thursday evening, I think. So when you submit the homework, just complete the survey as well. It just takes a couple of minutes. I do take a look at all the responses. So far, the ones that I've looked at, a couple of you are getting too stressed about in-class participation. That is completely counter to what the purpose of in-class participation is. Okay, don't worry about it. Last time the in-class participation, every one of them got 100%, right? So try to participate. I know once every 3 lectures can sometimes seem a bit too much. If you can't, as I mentioned, during the second half of the semester after spring break, I'll start posting very simple quiz. Whatever questions I ask in class, I'll just post it as a quiz. You'll just have to spend a couple of minutes to try and answer those so that you can compensate for the points you lost in the beginning of the semester. Right? So don't stress about it, don't worry about it. Everybody will likely get 100% for in-class participation. So just take it easy. It's just to get you all talking and getting comfortable in class, right? So the second thing is homework is due later today, tomorrow, Thursday. And again, if you're short on time, it's okay. The portal is open till Saturday. If you do submit it on time, I usually take a look at it later tomorrow night or Friday morning, and by Friday afternoon, I'll post comments. Just take a look. If there's some blatant mistake, you can fix it and submit it. Last time I posted the comments, I didn't realize I had to make the marks visible for the comments to become visible as well. So some of the comments I posted didn't show up until a later point in time. But I'll make sure I don't make the same mistake for the homework too. Right, and homework one, I just looked at everybody did most of the answers correct. Some of you had trouble, just a handful of you had trouble with Laplace transform or taking the solution for the ordinary differential equation. Those of you who are not too familiar with Laplace, I would recommend that during spring break you take the time and read through and familiarize yourself with solving differential equation using Laplace. Because when we go to control systems, designing controller, there is no way we can do it without using Laplace transform. Right? So we'll have to look at transfer functions and so on and so forth. So before that, make you very comfortable with it. If you haven't taken a course, I'm sure everybody must have done a course that taught Laplace transform. If you're not familiar with it, just come and see me during TRs or something, and we can, go over the theory. It's very simple subject to learn. All right. So as far as the homework is concerned, everybody did a good job for the most part. Most of you just took the weight that I gave. I just wanted to see what the variation would be in the class. One of you had 23 kgs, I think, which was the maximum. One of you had 2 kgs, a hammer. That was the lowest. So 23 kgs, the energy came out to be 345 joules. Anybody know how much kilocalories that would come out to be? Anybody know the conversion between calories and joules? So 1 kilocalorie is 4184 joules. So that's about 0.08 kilocalories. Right? So lifting that 23 kg from zero, which I definitely can't do until the top of your head, that's about a Tic Tac has about 2 kilocalories. Right? So you just spend less than 20% or even less than that by raising the weight. And my Chipotle bowl today morning was 2000 kilocalories. So there's no amount of weight you can lift to reduce weights. You'd have to do cardio or something like that. And whoever, you can pass it around. And whoever did the 2 kg hammer, they did put a lot of energy in doing the homework. Right, so so last class we were looking at Fourier transform, Fourier series, which is the homework that we have for this week. And
yeah, sorry, I just have a quick question about the homework. For problem 2, it asks for the steady state current. Do you want each harmonic individually, or just the sum of all of the harmonics in the DC?
So I was expecting each harmonic individually, and then I was hoping that some of you would add it up using MATLAB or something and show me the RC curve, the RL curve that you would get. But I would take any of the answers. Right? As long as you get all the harmonic components and just show the harmonic spectrum, that's fine too. But it'd be nice to sum it up. Any other questions? All right, so last week we were looking at Fourier series. There was one topic that I hadn't completed, which was Gibbs phenomena, which I will table it for now. We'll take a look at it when we discuss the homework solutions next Wednesday. Right? So today, this class, we will jump into Maxwell's equation. I hope all of you took the time to familiarize with vector calculus that you would have learned in your first year math. We won't get into too much detail of vector calculus, but we don't need to know it to be able to get into the math that would be required to understand how torque and force is produced in a motor. Right? So we have taken electromagnetic theory. All of these expressions should already be familiar to you. Those of you who haven't, don't worry too much about it. It's just a very short-time notations to the Maxwell's equation. Maxwell himself didn't have it in this form. It was thanks to Heaviside in the later part of 20th century who came up with this vector calculus to make a simplified representation for electromagnetic theory. Right? But our objective is to break down each of these equations into much simpler form with making a lot of simplifying assumptions so that we can then carry on this equation for the specific case of motor, how motors operate. Right? These equations give you all things about wave transmission, radiation, and all of those. We are not interested in any of them. Our only thing is when a current carrying conductor is in a magnetic field, what forces act on it. That's the only operating principle we've ever did. And so we're going to break down each of these equations into simpler expressions, and that's what we're going to carry on forward. Right? So those of you who have done the electromagnetic theory course, can you tell me what the name of the first equation is? What the laws? Divergence of electric field equal to charge enclosed, density of the charge enclosed divided by epsilon naught.
Gauss's law.
Gauss's law. Anybody else has any other answers? All right, the second equation, curl of an electric field equal to the negative time rate change of the magnetic field. We have already seen a different form of this expression in our first lecture. A changing magnetic field creates a voltage difference. Who found that out? Faraday. So you would have seen a different form of this law, E equal to d phi by dt, negative d phi by dt, or Lenz's law, right? So we will figure out how to convert this into that notation, right? But these are the fundamental laws though. Maybe you know what the third law is. The divergence of a magnetic field is equal to 0. What does that statement essentially mean? What was it?
The flux lines close in on itself.
Perfect. So there are no magnetic monopoles. Again, the Gauss's law for magnetics. No monopoles. No magnetic monopoles. The final equation, the curl of the magnetic field equal to is proportional to the current density enclosed plus the time rate change of the electric field proportional to the time rate change of electric field. What is the first half of this law? Who figured out the current carrying conductor creates its own magnetic field? Yep.
Was it Ampere?
Ampere's law. Dedicated with its own units. Then you know what the second half is. Let's call the displacement current. So that was the term that was introduced by Faraday. So when you have a capacitor and you connect it to a voltage source, a varying voltage source, some say tiny resistance, right? Because of the varying voltage source, there's going to be a varying potential across this capacitor, which means there's going to be a current through this capacitor. All right, now when we know if there is a current carrying conductor, on this wire I can put some kind of magnetic sensor like a coil or something and then measure what the magnetic field is. Right, and I can see as this current varies, the magnetic field will also vary. So if the current is varying sinusoidally, if this is the current, I can see the B also varies as long as the core has been saturated, so on and so forth. The B also varies similar to what the current is varying because of Ampere's law. But the interesting thing is if I put let's say this is like a can of some capacitor, aluminum can or something, and then I put a loop to measure the magnetic field there, I can see the magnetic field there is exactly the same as well. All right, but there is no current flowing through the capacitor in the traditional sense of the current. Right? We define current as the rate of change of charge, but this material itself, there is no charge flowing through the material. There is charge accumulating on this plate, There's charge discharging from the plate. Same thing is happening on the opposite side. Charge accumulating, charge discharging, but there is no charge flowing through the plates themselves. Right? If there's charge flowing through the plates, that means the insulation material has punctured, which is problematic. It's not going to operate as a capacitor. So the traditional sense, it is not carrying any charge, and yet we see a magnetic field when we measure across the capacitor. Right? This was quite a bit of conundrum as to what is really happening there. And that was addressed by this displacement current term that Maxwell introduces, which basically says that whenever there is an electric field varying, you would have the same phenomena as if a current was flowing through the element, and that's what you're measuring it as a magnetic field. For our case, the first simplifying assumption we are going to be making is that this component is very close to zero. So there are two reasons why this happens, because of the huge denominator that comes out, 1 by c squared, the speed of light, right, 200,000 meters per second square. So that's quite a bit of the denominator that we have here. So that is going to push this term to be very close to zero, unless E value is very large or the rate at which E is changing is very large. Right? In our case, both of that is not the case. So our voltages are typically not too high for a motor, so the Z value is not too much. And the second thing, the rate at which that voltage changes is typically like 60 hertz or 120 hertz, which is very, very small. You would see these radiations that come out of these varying E fields typically around gigahertz range, right? Your radio transmitters and all of those operate at very, very large frequencies, orders of magnitudes higher than what we operate our motors at. So at the low time rate of change of electric field, this term is almost going to be equal to zero on its own, and then divide by 1 by c squared. For all our purposes, for motors, we can assume that term is completely gone. So we're never going to look at displacement current. But even in case of motors, there are, when you do research on motor design and stuff, there are cases where this would become a problem. So when you have like a motor and you apply some voltage on it, there is this thing, when you are connected to a drive, there is this thing called common mode voltage that develops on the rotor shaft, which is a huge potential that builds up on the rotor shaft because of the voltage, the way you're operating your power converter. And that voltage can change quite fast, because the DT in case of power electronics can be very, very small, right? You can turn on and turn off your switch in a couple of 50, 60 nanoseconds in case of wide bandgap devices. So when this DT term becomes very small, even a moderate voltage can have significant amount of current flow through the system. So in those cases, we will start to consider it. But for an undergraduate course, you can consider this to be always zero for our analysis. And this assumption is very true for analyzing just the motor operation. Only for cases where you want to look at some leakage currents or stuff like that, you want to look into this component. All right, so that's the first simplifying assumption we are going to do. This term has disappeared for us, no longer going to be there. And we'll reduce all the others in a minute. What is this final equation called? Anybody? The fifth equation. It's not that equation all we have is fields doing nothing. Right? That's the final thing that actually puts real world action into place. We've already seen that equation too. Yep.
The Lorentz force equation.
Lorentz force equation. That's the Lorentz force equation, right? So the objective for today's lecture is going to be reducing these equations even further to a very simplified form that we can carry forward. And the two theorems that allow us to do, again, both of these are very simple derivations that you've probably done as a homework for your vector calculus course. So the first one is a Gauss theorem, which basically says that if you take a vector field and you integrate it over a closed surface, that is going to be same as the volume integral of the divergence of the vector field. So let's look at what that means in practice. So can somebody give me an example of a vector field and an example of a scalar field? A vector field and a scalar field. Let's start with the simple one. Any examples of a scalar field?
Temperature.
Temperature, perfect. So you have temperature, pressure, you'll get to voltage in a second. Voltage, all of these are scalar fields. So basically anything that does not vary depending on the direction in which you measure. If I tell the temperature at this point is 22 degrees Celsius, irrespective of which angle you measure it from or which direction you measure it from, it's always going to be 22 degrees Celsius. Right? It changes in different points in space, but it does not change from the direction which you measure. Anybody can give me an example of a vector field?
Velocity.
Velocity.
Like a compass or like a magnetic field?
Perfect. Magnetic field. 3 B field. E field as well, electric field. Anything else? Yep.
Gravitational pull around a planet.
Okay. Gravitational field. So all of these are vector field. So gravitational field is pretty easy to explain. Directionality of it. If I have a weighing scale and I stand on top of it, I'll see some measurement. If I put the same weighing scale at the same flow level but put it 90 degrees, I'm not going to see any weight measurement on it. Right? The weight experience is going to be 0. So gravitational field does depend on the direction. B field also depends on direction. Again, if you look at our Lorentz force equation, Q times V cross B, right? If I have a B field in this direction, and if I have a charge moving in this direction, right? The velocity of the charge particle is moving in this direction, and a B field that's like this, then there is going to be a force experience going from the V to the B. So it's going to be a force coming out of the board, right? So if on the other side, if we had another charge, capital Q going at this velocity in this direction, V cross B is going to be 0 in this case. Okay? There's only going to be dot product, cross product is 0. So depending on the direction in which the charge is moving, the force experienced by the charge is going to be different. So B field has a directional component to it as well. It matters whether B field is in this direction, or there is a component along all 3 different directions. Same goes with electric field as well. It is a component dependent field. And then velocity, let's look at fluid flow, for example. When you have some water molecule moving, right? If it's moving in this direction, there is a component of velocity along the x, there is a component of velocity along the y. Right? If you put this whole fluid in a pipe, the component of velocity along y goes to 0, there's only purely component of velocity along the x. So it depends on which direction the fluid is actually flowing. So anything that is dependent on the direction component, it could become a vector flow. Anything that is independent of direction component, we would have just pure scalar entity. So when we talk about all of those fields that I've written there, the E and the B, all of those are vector fields. So let's look at let's start off with a very simple case. We have a charge. Okay. All of you would have read this in high school, that you would have electric field radially outwards from this charge. We'll look at why it's radially outwards and not in any other direction a little bit later, but for now, let's take whatever you learned in high school to be the truth. Now what we're going to do is we're going to draw a sphere around it, a mathematical sphere, right? Just purely fictitious, imagine. And at every single point, we are going to assume the sphere is symmetric. So from this center point, it has a radius r along all directions. So the center is all centered around the charge. So it's somewhat reasonable to assume that the electric field at every single point is going to be exactly the same magnitude because of the pure symmetry. There has been no observation made so far that seems to indicate that electromagnetic theory seems to break symmetry. Right? There has been no such observation. Given that, it's reasonable to assume that every single point, if the charge is centered on the sphere, the E field is going to be the same magnitude irrespective of which point I measure it at. And given that this is perpendicular at every single point, I can now go ahead and derive the expression for the surface integral. So if I go around this mathematical surface, so this is the surface over which I'm integrating. Right? So I have a point charge and I have a spherical surface. It's a 3-dimensional spherical surface over which I'm going to integrate this electric field. My Gauss's theorem says that it's going to be equal to the volume integral of the divergence of the electric field. Now we know from Maxwell's first equation does this divergence of this electric field equal to charge density divided by epsilon naught. So that epsilon naught is just a constant. I can take that out, rho enclosed times dV. If I have a charge density and I integrate it over volume, what is that going to be? If I give you mass density, let's say a mass is 5 kgs per meter cube, and I ask you to integrate it over a volume of 1 meter cube, what is the mass going to be? This is going to be the mass 5 kgs, right? Mass times the volume over which you integrated. Same thing here. I've given you, so if you integrate mass density over a volume, you get the mass. You integrate charge density over a volume, you get the charge enclosed. So over this volume, if I give you the charge density over this enclosed within this volume, and I ask you to integrate over that volume, this result is basically whatever the charge that's enclosed. Q enclosed, right? So our surface integral, we still haven't figured out what the surface integral is yet. We will get to that, but we have figured out the right hand side of it. Q enclosed, charge enclosed, divided by epsilon naught, right? Permittivity of free space in 4 pi into 10 to the power minus 7. Oh, sorry, 9 into 10 to the power minus 12, roughly, or 8.857, I think, into 10 to the power minus 12. Right? So, this the right hand side. Is this part clear? How we got the Q enclosed by epsilon naught? Anybody has any questions? This is extremely difficult. If you don't understand me, let me know. We can go over it again. All right. So this part is the one that we need to figure out, surface integral of the electric field. So I'm going to stick to this half of the board. I'm going to retain those equations on the left. So let's look at what surface integral means. So let's say I have a surface like this, basically a sheet of paper. Okay. Let's say I have this sheet of paper, and then I have some kind of field, let's say B field or electric field perpendicular to the sheet of paper at every single point on this paper. So I have E at every single point. There is some electric field perpendicular to the surface. Right? And let's assume this electric field is not constant at every single point. So it's not here it's some value, here it's some value, here it's some value. Every single point it's some random value. But I can cut this surface into tiny areas. Right? Small areas. And let's call this DS1, tiny surface area, DS2, and so on and so forth, DSN. Right, such that I'm going to split this section, split this piece of paper into tiny areas. Right, and within each of these areas, I'm going to split it in such a way that the electric field from within this area doesn't change that much. All right, if it does change, then I'm going to split it into even smaller sections. Right. So I can keep on splitting it into tinier portions until the electric field across that tiny area that I've chosen doesn't change. Okay. Now, what I'm going to do is I'm going to take, let's say the electric field here was E1, electric field here is some E something, here electric field perpendicular to this area is E2, so on and so forth. So I'm going to take the product of the electric field at every single tiny area that I have and sum them up over the full surface. All right, for all the elements that are within the surface area. Everybody clear so far what I'm trying to do? Okay. So now if I let this tiny area go towards 0 such that it becomes extremely small area, then the above summation converges to the surface integral that we have there. E dot ds. So that's all the definition of a surface integral. Right? Same as when we did regular integration, you would have used the trapezoidal approximation, and if the trapezoidal width has become extremely tiny, if it's infinitesimally small, then it just converges to the integral of the curve. Same here. So you take the electric field at every single point, tiny area, multiplied by the cross-sectional area, right? And then if the cross-sectional area itself is made very small, or basically an infinite number of these elements, then the summation would tend towards the integration, right? And if you do this over a closed surface area, so this was an open surface area. If I do this over some closed surface area, then basically represented by this closed symbol, that's all. Okay, everybody clear? So, So we have our left-hand side expression. Surface integral E dot ds is equal to Q enclosed by epsilon naught. Now I said the electric field over that sphere, every single point of the sphere is the same, right? I chose a sphere that's symmetric around the charge, and because the laws of electromagnetic theory seem to abide by laws of symmetry, it is a reasonable assumption that the electric field on every single point is going to be the same. So I can pull the z component outside. It's a constant value at every single point on the sphere. Surface integral of the sphere, U enclosed, divided by epsilon naught. What is this term going to come out to be? What is the surface integral of a sphere? All of you know the answer. Why is
Q
just
pi r,
what was it?
Q pi r.
That would give me the surface area of a circle. So the way I drew it, it looks like a circle, but it's a sphere. Right? So surface area of a sphere would be
4 pi r cubed over 3.
4 pi r squared. You're looking at the volume. So 4 by 3 r cube would be 4 pi by 3 r cube would be the volume. So surface area of the sphere would be 4 pi r squared. So our electric field is going to be 1 by 4 pi epsilon naught Q enclosed divided by r squared. So this is the electric field at every single point on the sphere for a sphere at a given distance radius r. So if I double the radius, then the electric field at that point would be 1 by 4th of what it was at the previous radius that we considered. Right? Everybody clear so far? Okay. Now, what is going to be the, so let's say I have the charge there. I have the positive charge. Let's call that Q1. Right? So this is going to be Q enclosed. I'm just going to leave it away. So the electric field due to charge Q1 at some distance r is going to be Q1 divided by 4 pi epsilon naught r squared. And if I now introduce another charge Q2, okay, so the electric field here due to Q1 is now going to interact with this newly introduced charge Q2 to produce a force given by the Lorentz force equation, which is going to be Q times E. So the force is going to be force on charge Q2 due to charge Q1 is just going to be the electric field due to charge Q1 times Q2. Right? So that's how you get your formula Q1 Q2 divided by 4 pi epsilon naught r squared. And what is this law? Coulomb's law. Thank you. Basically, your Gauss's law, the first equation for electrostatics, and your Lorentz force equation, the first half of it, or the force equation for purely electrostatic case alone, combined would give you your Coulomb's law that you have learned as a fundamental law. All right, but it's basically two fundamental laws that are hidden behind this one single equation. Right? Everybody clear so far what flux, what surface integral is? Okay. So, the second one. So the way I constructed this area, that is totally irrelevant. So I could have had a charge like this. I took a nice sphere just to make my life simple. But you can consider a odd looking shape. It really doesn't matter. Even for this surface, if I go around the loop, integrate the electric field at every single point, the value is going to be equal to the charge enclosed divided by epsilon naught. What was the reason I considered a sphere instead of this?
It's just hard to integrate. It's an odd area.
Okay. So it's harder to integrate in this case, particularly because I can't make the assumption when I took a sphere, a symmetric sphere, I could make the assumption that the magnitude of the electric field at every single point will be the same, right? Because it's equidistant from the center of the sphere. But in this case, I can't make that assumption. So E is not a constant that I can pull out of the integration and just make it an integral of the surface area. If I know the equation for this curve, then I can easily integrate the surface area of this curve. That is not the problem though. But I cannot make the assumption that E here E1 is going to be equal to E2. That assumption fails. In this case, E1 was equal to E2. Here they are not equal. So I cannot pull the T out of integration and just make my life more complicated. And that's the reason we consider this sphere for solving the problem. But once you know the electric field at every single point, you can go back and do the math and verify that irrespective of what shape you take, you go around and integrate the electric field, it will always be equal to the charge enclosed divided by the epsilon naught. Right? So for our case, we want to get a more intuitive feel for what is actually going on. Because as I mentioned in the first lecture, the machines is as much as an art as it is math. So let's try and see if we can get an equivalent representation from our real world experience, even though it's very fundamentally flawed, as we'll see, but it does help give an intuitive feel for what's going on. Let's say you're sitting next to a campfire, right? And then let's say you create some kind of shell that you cover the campfire with of some radius R1, such that this shell can capture all the energy coming out of this campfire. And then let's say I make another shell, which is a little bit bigger, of some radius R2, which in the absence of shell L1, R1 can collect all the energy coming out of the heat source that's in between, that's in the middle. Right? The amount of energy that's collected by this shell or this shell is going to be exactly the same, equal to whatever the energy is coming out of the source that's inside. Right? The same thing is happening irrespective of what shape you consider construct around the charge, as long as it encloses the whole charge and you collect all the flux coming out of it, it is going to be directly proportional to whatever the heat source that's coming in right in the middle of the whatever caused that heat flux to come out in the first place. Right? There is a big fundamental flaw in making this kind of simplification. Can you give me what it is? A physics textbook would never give you this equivalence because it's extremely faulty. What is the reason why the heat here must be the same as the heat here if I collect all of them? What is the fundamental law?
Conservation of energy.
Okay, conservation of energy. So irrespective of whether I collect all the energy here or here, in between the process, energy hasn't been destroyed. Right? So whatever energy is here must be the same energy here as well. But when you look at electric field, there is no such thing like conservation of electric field or any such concept. Right? It's just similar to how conservation of energy is fundamental to itself because of the symmetry of time. This electric field, the surface integral of an electric field over a closed surface being proportional to the charge enclosed is a fundamental law of nature. Alright, we haven't found anything more fundamental to it than that to explain why it's happening. Alright, so that's the reason why this comparison is never given. But again, for our case, it's more important that we get an intuitive feel for what's going on rather than being extremely crude to the mathematics of it. So this is an easy way of imagining what's actually going on. So you take some source that's radiating something, again, radiating in the colloquial sense, not in electromagnetic radiation sense, and you construct a sphere around it. If you collect all of it that's radiating outwards, that must be equal to whatever is causing the radiation in the first place, right? So, any clear? Do you have any questions? Right? So the second thing we're going to be looking at is the case where we have these charges oddly placed. So this property that divergence of a vector field proportional to whatever is enclosed, some density that's enclosed. That is not just true for electric field alone. In electric field, it ended up being divergence of the electric field was rho enclosed by epsilon naught. It is also true in case of, say, gravitational field. In case of gravitational field, so in this case, it was charge density. In this case, it's the mass density. And this is fundamentally true for any kind of field whose force follows the inverse square law. The field follows that inverse square law. Right? In a three-dimensional world where fields follow that inverse square law, all irrotational fields have this property that the divergence would be proportional to whatever the source is causing that field to be there in the first place. Right? It's an interesting piece of math. But okay, so let's look at the case where we have two charges separated by some distance 2d, and we have another set of two charges which are separated by a distance d. In both cases, I construct a sphere of some radius r, same radius in both cases. If I do the integral of electric field in the first case, E1 ds, surface integral over the sphere, and if I do the surface integral of the electric field in the second case, what would be their values? Would they be the same? Would one of them be twice the other? Would it be half? 4 times? Anyway, yeah,
Should be the same.
should be the same. So irrespective of what's going on inside, right, if the total number of charge enclosed is exactly the same, our formula again mentions that it's just Q enclosed by epsilon naught. Right? It doesn't matter how your charges are placed within the sphere, what kind of combination. You could have another negative charge and another positive charge. These both would effectively just cancel each other out as long as you go around the whole sphere and integrate the electric field. But it must be noted that the pattern of the electric field due to these set of charges is not going to be the same as the pattern of electric field due to these set of charges. Right? If you look at the electric field at every single point, this will definitely not be the same as what we have from here. It is just guaranteed that if you go around and integrate the electric field for this case and also integrate the electric field for this case, the integral would end up being the same. Individually, E1 is not equal to E2. Just because the integral is the same, that doesn't mean E1 is equal to E2. That will definitely not be the case unless they are exactly placed the same. Okay.
And then it also doesn't matter like where the charges are within the. Okay.
It won't matter. We'll get to that in just a second. Any other questions? So let's look at the cases. So let's look at the case where take a charge Q and let's put it in a sphere in a place where it's not in the center. Once again, if I go integrate the electric field, it is going to be Q divided by epsilon naught. Can everybody give me an intuitive reason for why this is the case?
As like at the opposite edge of the circle, it'll be weaker, but it'll be balanced out by the other side.
Perfect. So if you take a constant steradian constant cone of angle, this angle is same as this angle in the 3D. So this is a 3D sphere, not a 2D case. Right? So it's a cone that is having this angle. Here, if you look at the electric field, let's call this radius R1 and let's call this radius R2. The electric field here is going to be equal to Q divided by 4 pi epsilon naught R1 square. Electric field here E2 is going to be equal to Q divided by 4 pi epsilon naught R2 square. But if you look at the surface area here, so the surface area ds1, that is going to be equal to proportional to 4 pi R1 square, right? Well, the surface area of this section of the sphere, ds2, is going to be proportional to 4 pi R2 square. So the product of E1 times ds1 and then product of E2 times ds2, right? So this 4 pi R1 square, the denominator cancels out with 4 pi R1 square on the numerator from ds1 and this 4 pi R2 square cancels out with this 4 pi R2 square on the denominator, right? So in both cases, you end up with Q divided by 4 pi epsilon naught as you go around the sphere and integrate it. So that's why the position of the charge really doesn't matter as long as you enclose the hole with a closed surface and you integrate, it's always going to be equal to Q divided by epsilon naught. Maybe any questions? So that covers our first equation. So the second one we are going to be looking at is our let's skip the second equation for just a minute and jump to third one. It says divergence of a magnetic field equal to 0. Since we are on the topic of divergence, that's completed. So what does that mean? If I substitute back into our Gauss's theorem, which I had before, so we go around Again, this is not a law, this is a theorem. It's a very simple derivation. I'll post it on Canvas if anybody is interested, or after class, come and meet me, we can derive it. So if you go around and integrate the magnetic field, it must be equal to the volume integral, closed surface, must be equal to the volume integral of the divergence of the magnetic field. So where B is the magnetic field. Does anybody know any other name for magnetic field? So if you're from machines design background or something, you'll probably use a different name. Even in electromagnetic theory, you might have been given a different name for magnetic field. Sometimes referred to as magnetic flux density. Both of them are the same, it's the same B field. So let's substitute here that expression that we have. So volume integral of 0 dot ds. So 0. So what it basically says, if we go around a closed surface and integrate the magnetic field, the result is going to be 0. So let's see what that means. So let's say I have a bar magnet. Let's say it's outside. It used to commonly use sign convention where north to south is the field lines. What is going to be the direction of the field lines within the magnet? Maybe north to south, south to north. Inside the magnet,
Base south to north.
south to north. We can take a look at it why in a second, what fundamental law proves that. But for now, let's look at a sphere that's constructed, a mathematical sphere that encloses the magnet like this. All the magnetics of Gauss's law for magnetism says is that if I go around and look at the B field at every single point that's perpendicular to the surface that I've drawn and integrate it to the surface, this must be equal to 0. What in essence it says is whatever field lines leave this sphere must be the same exact number of field lines with the same strength that comes back and terminates. Right? So that basically means you can never have a monopole like we had in case of charge. In case of charge, we had a positive charge which was always radiating outwards, a negative charge which was always having field line terminate inside it. Right? But in case of magnets, you can never discover just a pure north pole alone, which radiates B field in all directions. This has not been discovered, right? So there are no magnetic monopoles, and that's exactly what this law proves, because whatever field line goes out always comes and terminates. If you were to cut this magnet into half, you would end up creating two new magnets with north and south, right? So it will always be such that whatever field line goes out comes in. So why do they have to go from south to north inside? Because this is whatever I've drawn here is just a pure mathematical surface. I can draw a mathematical surface that cuts through half the magnet. Okay? So even in that case, this law is a fundamental law and it must be obeyed. Surface integral B dot ds must be equal to 0. So on the top half field lines are going out, in the bottom half also if they start to go out, this law cannot be satisfied. So whatever field lines went out must return back through the magnet from south to north. Right? Everybody clear? Anybody any questions? So let's define a new term, flux. Let's go back to the simple case of a rectangular sheet. And let's say I have a B field perpendicular to the sheet at every single point. So this has some surface area A, cross-sectional area. And then we have some magnetic field which is constant at every single point. I can figure out what the flux is going to be, which I'm defining Okay, this is the definition. Yes, surface integral B dot ds. Alright, notice I'm not putting a closed surface integral. What will happen if I do closed surface integral? What will be the flux? If I take a closed surface and integrate the B field, what am I going to get?
0.
0. That's what we just saw, right? There are no magnetic monopoles. Gauss's law of magnetism. So if I do this over a closed surface, this flux is going to be 0. So that's why I'm considering just an open surface like this. And if I integrate this magnetic field, I'm going to call this flux or magnetic flux. What will this be in this particular case that I've shown? What is this value going to be? B is a constant, the area I've given, what is the value?
E times area.
B times area. Just because B is constant, alright? If B is not constant, of course, I cannot pull this term out, and this integral cannot just be done as area rule. So this is our flux, and this is the reason that B is sometimes called magnetic flux density, because B is just flux per unit area, right, in this particular case. So hence the name flux density. So the term density is somewhat confusingly used in different cases. Typically, we would associate density with volume, right? When we have mass per unit volume is considered mass density. But it's also used for per unit area, it's also used for per meter. For instance, when you have a line charge, right, you do define line density for the charge, which is just charge per unit length. And similarly, when we have this magnetic field, flux per unit area is defined as flux density, right? So the density term is thrown around for all dimensions, starting from length, area, and as well as volume. So in our case, magnetic flux density is basically defined as the flux divided per unit area. And this name comes for historical reasons. Typically, we nowadays like to use magnetic field, but this name still sticks around, particularly when we look at Machine's book. And the reason is that back in the day, people didn't know that B field is real. Right? When Faraday put those iron filings and drew the field lines, it was basically considered to be a mathematical invention created to just explain what's going on. It was believed flux was what was real. Because when we have the heat case, we can feel the flux coming out, heat flux coming out of a stove or a campfire or whatever. Right? So it was thought of in like fluid flow, heat flow kind of sense, and it was believed that flux is what was real. And these B field lines were just drawn as a mathematical way of demonstrating them. But as you will see, this B field is very real because that's where the energy is stored in case of an inductor or something. The energy is fully stored in the B field. It's not in the material, it's not in the metal or anything, it's in the field itself. So these are absolutely true and real. They are physical entities. So both the term magnetic field has stuck as well as the old way of talking about magnetic flux density. Right? So we are going to do a couple of simplifications. Yep.
So is a field just like a energy storage in space almost?
It's more than just the energy storage because when you have a field, there is an associated energy with it. Right? When you have a magnetic field, we have that equation, right? 1 by B squared divided by 2 mu naught. And when we had electric field, it was epsilon naught E squared by 2 when we looked at the first lecture for electrostatic motor. So there is an energy associated with the field. But even otherwise, there are forces that come about when you introduce a charge in a field, which are independent of the energy themselves in the field. So it's more than just the entity that stores energy. And there is an energy associated with the field, but it's more than that. So it's like, let's say you take a ball on top of a mountain, right? Some height. There is a potential energy to it, but the ball is more than just the potential energy. Right? There is more to that other than just the energy that's stored in the field. Right?
It's like energy plus other information.
Yep.
Okay.
That has other physical attributes that come about. Right? And because there's more, so like once this field starts changing, it has secondary effects where it creates other fields. Right? And both of these start to interact with one another, it creates radiation, which is another transmission of energy. So there are a whole bunch of other things that go about secondary impacts that it has. Right? Any other questions? Okay. One more critical thing is that this field that we just saw, so whatever lines that I drew here, these are not discrete. Right? So when we think of field, like these lines do not think of it like molecules of water be moving with some velocity v. When we think of it as fluid flow, those are discrete entities. When we think of velocity vector, those are discrete entities associated with discrete molecules, right? So we can draw discrete lines for those vector field. In B field, there is no discretization of B field. Every single point in space, there is going to be some B field. Right? There is no medium required for B field to transmit. That was the famous experiment, right? Michelson-Morley experiment that he conducted in early 20th century, where he showed that there is no ether. Vacuum is just pure vacuum. Light can transmit through vacuum. Because before that, waves were thought of to be needed a medium to transmit. Sound wave requires a medium to transmit. Heat wave requires a medium to transmit. All of those require a medium to transmit. Electromagnetic waves, on the other hand, do not require a medium. That also means they are not bound by the discrete limits of what a medium can do. Right? So every single point that I draw these B fields, these are not discrete. Just think of them like a temperature curve or some. Even in case of temperature, it's like points where the molecules are vibrating. That's what is temperature. But in case of B field and E field, it's at every single point there is an associated B field. When I draw these lines, and every single point there's an associated E field. Right? So we have simplified. So let's go ahead and simplify some of these. So this is gone. You don't have to remember this form anymore. So let me delete off the displacement equations that is gone as well for us because it's so tiny. So this we are going to replace with a new definition. Flux, which is equal to surface integral v dot ds. And if I look at this flux over a closed surface, it's always going to be equal to 0. Right? So this is our new equation going forward. And this we simplified using the Gauss's law. The first one, we will get to it. We don't need this at all, but we use this as a way of understanding what's going on here because all of us are familiar with it. Again, in our case, as I mentioned, we are not going to be worried too much about the electric field that is within the machine. Right? We will be worried about the electric field and the impact of it outside of the machine when we apply the voltage and potential, but within the machine it has absolutely no impact. So even when we pass current through the motor winding, when we apply voltage across the motor winding, there are currents and there are charges that are moving, but there is no charge differential. Right? So the charge is moving, but there is, if you take any section of the motor and cut it, you are not going to see a discrete amount of positive charge separated from a negative charge. This is not a capacitor. Right? So there is no concept of electric field that's introduced on a macroscopic level in a motor. Alright, so in a minute we'll delete off this equation, but this is the equality equation for the third one. Now next what we're going to do is try and simplify this fourth equation. 3, 2, 1. So let's go ahead and simplify fourth one. So for that we're going to be using the Stokes theorem. Again, an extremely simple theorem, two-line derivation pretty much. So what it says is if you go around the loop and integrate any vector field, that is going to be equal to the surface integral of the curl of the vector field. So we already saw what the curl surface integral means. Now let's try and see what a line integral means. So let's say I draw some loop and I have some field that looks like this. So what I'm going to do is let me look at this tiny cross section and let me draw that here. Right? I'm going to look at what the field looks like at every single point. I'm going to take tiny segments similar to the previous case where I took tiny cross-sectional area ds1, ds2, so on and so forth. Here I'm going to take tiny line segments dl1, dl2, dl3, so on and so forth, such that within this segment, the vector field that is there on in that segment is not changing. If the vector field is changing in that segment, what can I do? I can cut the segment even finer, right? To the point where it gets so fine that the whatever vector field I'm considering does not change in the tiny segment that I have. Then, if I look at the value here, let's call it V1, let's call the value here V2, let's call the value here V3, and even within this, the values that I'm in, so let's say I have a line segment like this, and there is a vector field like this. The only component I'm interested in is the component that's tangential. Only the component that's tangential I'm interested, component that's perpendicular I'm not interested in. Right, so it's the dot product, B dot dl. So it's the dot product of the vector field with the line segment that I have, right? So if it's along the direction of the line segment, I will do the integral, consider it in the integral. If it's perpendicular, I'm not going to consider it. Purely a definition of how I'm going to define line integral is, all right? Just a definition, nothing more. So if I do this summation now, if I look at V1, T1, DL1, assuming that all of these are tangential to the line segment that I had, V2, DL2, V3, DL3, or let me make it more clear by just putting the perpendicular symbol here. Only the perpendicular component matters. Dot, 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 Dn, the DLN. If this line segment tends towards 0, if I make the line segment so tiny such that the number of elements become infinite, this tends towards the line integral. Right? Everybody clear what a line integral means? Same as what we did with surface integral. In surface integral, we took tiny areas, multiplied with the field, whatever was perpendicular to that area, and summed all of those. If I make those areas small enough, infinitesimally small, such that the number of elements become infinite, it converges to the surface integral. Here it converges to the line integral if I do the same for line segments. Right? So let me substitute my fourth equation into Stokes' theorem. So if I go around the loop, integrate the B field, it has to be equal to the surface integral of the curl of the B field. Right, so the curl of the B field is mu naught, which is the permittivity of free space, permeability of free space, sorry, 45 into 10 to the power minus 7, right, mu naught times J enclosed, which is the current density. So J enclosed is current density, and somewhat confusingly again. So if I have some current I flowing through this conductor with a cross-sectional area A, the current density J is equal to I by A. In this particular case, where the charges are perpendicular to the surface area, if the charges are moving perpendicular as well as in other directions, then it's just the perpendicular component alone that would matter, not the rest of it. Right? So the current density J is the current that we have divided by the cross-sectional area. So this unit is meter square, or ampere per meter square. So once I substitute those there, so it's surface integral, mu naught is just a constant, I can take it out, J enclosed times ds. What would that give me? If I integrate current density over a closed surface, when I integrated the charge density over a closed volume, I end up getting charge enclosed. When I integrate current density over a closed this surface, open surface, what do I end up getting?
Current density,
Yeah, that's what I'm integrating. What do I get?
you just get current then.
I'll get current, thank you. So that ends up being I enclosed, mu naught times I enclosed, right? So it's current divided by per unit area. And if I multiply the area back up again, I end up with the current term as the end result. Okay. So we are now going to delete off the fourth equation and replace it with this new form that we have. So this is gone as well. So our new representation for Ampere's law is integral, line integral over a closed loop, d dot dl is equal to mu naught times I enclosed. So let's try and get an intuitive feel for what's going on. So first, let's start off with the K is what it actually looks like and what it means. So if I have a current carrying conductor, again you can figure out how the B field is going to be by using the right hand thumb rule. It's a rule, not a law. The underlying law is this one. Okay, so the B field is going to look like this, tangential at every single point. We'll get to the reason why it's not radial. Okay, so it's going to be tangential at every single point. With a constant radius from the center of the conductor. Alright, assume that this is the shape that we have. We can do this experiment very simple to figure out. So you take a current carrying conductor, put it through a cardboard, put a hole in a cardboard and put the conductor, drop some iron filings, you'll see rings form around, right? Again, those rings will form at discrete points. That doesn't mean B field is discrete. It is just that the affinity, the material iron filings just tend to attract to one another, so they bunch up in such a form, but it actually spread through the plane, right? So if we go around this loop that I have drawn here and integrate the B field over this closed loop, this would be equal to the current enclosed, I enclosed times mu naught. In this case, I enclosed is just the current through the conductor I. Right? Same as the explanation that I gave for a charge. When I took a symmetric sphere at equidistance from every single point in the sphere, it is reasonable to assume that the electric field is going to be constant at every single point. Similarly, if I take a loop that is equidistant such that it's centered around the conductor and it's equidistant at every single point, it is a reasonable assumption that the B field will be the same magnitude at every single point, right? Purely due to symmetry. So this B is going to be a constant around this loop that I've chosen because every single point the radius is on. Right? So B can be pulled out. We go around the loop, integrate, equal to mu naught times I. What will this integral give me? Somebody already gave me the answer for that. When I asked for surface integral. What was the line integral for this loop that I have considered? It's a circular loop. 2 by R, thank you. So which implies B is going to be equal to mu naught I divided by 2 by R. So if I go a little bit farther away and look at what this, so let's call this B1, let's call this B2, let's call this R1, and let's take a radius R2. B2 is going to be much smaller than B1 by a factor of R2 by R1. Right? So as I go farther and farther, this radius becomes bigger and bigger, the B field starts to become smaller and smaller, weaker and weaker. Okay, so let's try and get a intuitive feel for what's going on, same as what we did for the case of a charge with the campfire. Here too, again, the physics of it will be fundamentally wrong, the comparison, but it gives a way to remember what's actually going on. Right, so let's consider the case of a whirlpool. Let's look at the water molecules surrounding that whirlpool. So this is a drain. Have anybody seen a whirlpool? All of you must have, right? When you drain a bathtub, when you drain a sink, you would have seen it pretty much on a day-to-day basis. Have anybody been to a hydroelectric power plant? Site visit? Oh, you definitely should. Those of you who are shaking, no. Very interesting. So whenever they open the floodgates, you can see a huge whirlpool form wherever they're opening the floodgates, and the speed at which those water molecules are rotating in that whirlpool is going to be definitely way faster than when you drain your bathtub, right? Because the speed at which it's rotating is going to be proportional to the rate at which the water is draining out, right? So if I look at the velocity of the water molecules, let's say at a constant radius, some radius R1, let me call it V1, and then I'm going to look at the velocity of the water molecules at some radius R2, traveling at some velocity V2 in that particular area. So you can, some of you might have done this as kids, right? When it rains and then the drain is draining, you will put twigs on the circular, the water that's circulating, and you can see the twigs circle around. And if you drop the twig closer to the drain, it will circle faster because the water molecules is traveling faster closer to the drain. Right? So if you go around and integrate the velocity with which the water molecules is traveling at any particular loop, so let's say L1, and let's call this loop L2. This is going to be proportional to the rate at which the water is draining. Right? So in case of a whirlpool, this water is draining thousands of liters of water per second compared to just a few liters of water per second, or even not even liters of water per second in your sink or your drain. Right? So when the volume of the water being drained becomes larger, the velocity with which the water molecules move around also becomes larger. So if I go around the loop and integrate the velocity molecule for a whirlpool in a hydropower plant, that's going to be far greater than compared to what you'll get when you sink or you bathtub. Right? So it's going to be proportional to the drain rate. And we'll get to a second why it's going to be proportional to the drain rate. But this is exactly the same as what we get in a case of a magnetic field. If you go around the loop, integrate the magnetic field, it's going to be proportional to the charge drain rate. Right? Which is just dq by dt, which is your current. So whenever you have a current carrying conductor through which charges are draining, the magnetic field that surrounds the current carrying conductor go around the loop, integrate the B field, that's going to be proportional to the rate at which the charges are draining, which is equal to your current. Anybody have any questions so far? Okay. So let's see what's going on in case of the drain again. So let me construct a mathematical sphere, and then in the middle there is the drain through which water is draining, and then there are water molecules all over the surface which is just circulating around. And if I construct a bigger surface around this drain, so I have a pipe through which it's draining, and I'm constructing a mathematical cylinder around it so that I'm enclosing all the water molecules, and then I'm constructing a bigger cylinder, and I'm going to analyze what the water molecules are doing there compared to what it's doing on the inner cylinder. Okay. So if I look at the inner case, the rate at which water is passing through the surface, so let's say the volume, the length of this is L, the radius is R1. The length again here is L, I'm going to consider the same vertical structure, but the radius is R2. So the rate at which water is passing through this inner volume is going to be equal to 2 times pi times R1 times L, the volume, times the velocity, the surface area of the cylinder, times the velocity with which the water molecules are traveling on this surface. So let's call this V1, let's call this V2. Now I'm going to make a bold claim that these two terms must be equal. Can anybody tell me why? When will it be equal? When will it not be equal? So this is the rate at which the water molecules is moving past the surface, right? At some point in time, the same set of water molecules is now going to go to the drain. And then water molecules here is going to go into that surface, right? Given an incompressible fluid, whatever water molecules is passing through this surface must be the same water molecules, same set of water molecules passing through this surface sometime later, must be the same set of water molecules that after some time get drained through this drain. Okay? So the rate at which the water molecules is passing through one surface is going to be equal to the rate at which water molecules passes through the other surface, which must be proportional to the rate at which the water is draining. Right? So if I am closer, if R1 is smaller, then V1 has to be larger so that when R2 is larger, V2 will be smaller so that this product R1 V1 is always equal to R2 V2. Same in our case, V1 R1, in case of a conductor V1 R1 is equal to V2 R2. Right? Which in turn again V was proportional to the current that's flowing through the conductor, same as the charge drain rate. Right? Everybody.
So don't you have no flux inward because your velocity is parallel with tangent with the surface?
There is also, that's where the problem in our assumption comes into picture. So there are two mistakes in this model. First thing, I assume the velocity component is always tangential. There's definitely going to be a component that's radially inverse, otherwise there's not going to be drain at all. There is a tangent, so there's a component of velocity which is almost like in a angle form. We are making a simplifying assumption that the rate at which it's radially going inverse will be the rate at which it's tangentially moving as well. So that's the first assumption. In case of a magnetic field, we are never going to have this radial component. Can anybody tell me why in case of a magnetic field, we are never going to have a radial component? We already saw what law that was. When I do this magnetic field for a current carrying conductor, I do it perfectly tangential. Why isn't there a radial component?
The divergence is 0.
Perfect. So divergence is 0. So let's say I have a radial component for somehow, however it comes about. So if I had some current carrying conductor in between, and instead of the magnetic field being perfectly tangential, let's say it had some angled component like this, similar to what I had in case of the water flow, then I'll always be able to construct a surface. If I enclose a mathematical surface like this, I have B field that's always coming in with no B field going out. Right? That would mean integral B dot ds is equal non-zero value, which would violate my third condition. So in this case, if I do the surface integral of B dot ds, this is not going to be equal to 0 because all of these components are going inward, right? For the surface that I have considered. So that would be a violation of the third law. That would mean there is some kind of south pole that's attracting all of these to drain towards it. Alright, so the only solution, again, the same thing would be that it can't have a component that's going outwards either. That means there's some north pole that's pushing out without an equivalent south pole. So the only solution that we are left with this condition is that there is only purely tangential component. Right? So whenever a vector field has its divergence equal to 0, the vector field will only have purely circulating components. It won't have any radial component. Now let's go back to the case of an electrostatic charge. I said the fields are only purely radial. Why couldn't an electrostatic field create a component like this? Why couldn't I get a circulating component in an electrostatic field?
Is it not symmetric?
Okay, I can still make it symmetric. Here also, right? When I have a current carrying conductor, this is a beautifully symmetric curve.
But in 3D, you can't make it symmetric, right?
In 3D, I can still make it symmetric in 3D. I can create like, so think of this as a circle, right? And if I rotate the circle in 3-dimensional plane, I can create a symmetric circulating vector too. It would have a component to it. It would be either clockwise or anti-clockwise, but I can still create a symmetric one. So if there is a circulating component, that would mean this component, the curl. So if I go around the loop, integrate the magnetic field, right? So this is where, how did I get this? Curl of the magnetic field was equal to mu naught times I enclosed. Right? This is what ended up becoming integral line integral B dot dl equal to some component. But if I go to this equation and I see when I have a charge, there is no magnetic field. It's a pure electrostatic field. Right? When there is electrostatic field, there is no B and there is no varying B. So dV by dt term is 0. So when there is no varying magnetic field, the curl becomes 0. If the curl becomes 0, the line integral over the loop becomes 0 from Stokes theorem. So if the line integral is 0, there cannot be any tangential component, there can only be radial component. Because if there is a tangential component, the line integral will be non-zero. That means the curl will end up being non-zero. That means there has to be a time varying magnetic field, but we know that the charge does not create time varying magnetic field. Right? So this is the reason that we don't see that in the case of an electrostatic field. Right? Do you have any questions? Okay, so magnetic field. Case where anybody wants me to repeat anything, let me know. This is an extremely critical topic. If you don't get an intuitive feel for this, learning machines later will become very complicated. But if you get an intuitive feel for all of this content, machines are just extremely easy. It's like basic first year circuits goes after this. Right? This is the most complicated part of the course. Afterwards, it will be very smooth sailing if you understand this, otherwise it will become a nightmare. Anybody want me to repeat anything? Be very clear. Okay. There's one more area. So Ben mentioned the first place where our equivalence fails is that in case of magnetic field, it's always tangential. Right? There cannot be a component where we have components that are non-tangential to the surface because of the current that's carrying. There's another problem in the another flaw in this comparison to that comparison. When I said that the flow rate of this cylinder must be same as the flow rate of this cylinder must be the flow rate of the drain. What principle was I using? What law was I using? In case of the campfire case, I use conservation of energy. What am I conserving here when I say water molecules on the outer cylinder must be the same as the water molecules on the inner cylinder must be the same, draining later as the pipe. Yep.
Conservation of angular momentum.
Conservation of angular momentum. In this case, I'm not using conservation of angular momentum. What else is conserved? This is clearly not conservation of angular momentum because what was previously rotating is now draining down, right? So, yep.
You said it's an incompressible fluid
Yep. So, what am I conserving?
volume, maybe.
Right? Clean. Right. So, conservation of mass or basically conservation of volume. So, I'm assuming that the density is constant. It will be effectively conservation of mass. Right. So, whatever mass of water molecules I have here is the same mass of water molecules that I have here. The same mass of water molecules that I have to go out of this pipe, same rate at which the water molecules go out of the pipe. So that conservation would prevent it from being violated in this case. In our case, again, we feel there is no such conservation principle that's making it hold. All right, there was again some fundamental law that was making it conserved. Here, there is no such case to make the kind of similarity. That's the reason, again, in physics book, you won't see the comparison, but in our case, it's very important that we get a intuitive feel for it so that it becomes easier as we go forward. We have just one more minute. Let me clear up one more thing. So previous case, I had a current carrying conductor and I drew the current carrying conductor at the center of the loop. Let's say if I move the current carrying conductor a little bit farther away so that it's not centered. If I go around and integrate the B field, will it still be equal to I enclosed? Okay, that's again a fundamental law. If I go around and integrate B field, irrespective of the placement of the conductor, it is going to be equal to I enclosed. We can do the same analysis we did before, where we can take an angle, equal angle on both sides. Right? Here the magnetic field is going to be I divided by mu naught I divided by 2 pi R1. Here it's going to be mu naught I divided by 2 pi R2. But if I look at the DL here, that is going to be proportional to 2 pi R1, right? The circumference here. And the DL here is going to be proportional to 2 pi R2. So again, these two products get cancelled out in the numerator and the denominator when I do B dot DL. So it's always going to be again the same mu naught times I enclosed. It does not matter where your current carrying conductor is. In a loop, you'll get the same magnetic field. This is a common question that students have when they do current measurements in the lab. You might have seen a clamp meter that you use when you have a current carrying conductor. The way you measure the current is you put a clamp around it, which is basically a coil that measures the magnetic field. Students, when they initially begin, they usually try to center the conductor in the middle of the clamp, thinking that that somehow matters. It does not matter where the conductor is in the position of the clamp. It is always going to get the same amount of magnetic field when you go around the loop and integrate it, so that the current that you measure is going to be same irrespective of which position the current conductor is in the clamp. Right? With that, let's end today, and then we'll continue again on Friday. I'll repeat this again on Friday so that it kind of gets reinforced, so don't worry too much. But those of you who are not familiar with vector calculus, please do compare yourself with it.